Okay, so let's look at the probability of collision in a hashing function. Just a quick recap of what a hashing function is. Any function denoted by h of k, and by the way, you don't have to denote it like this. I'm doing it right now. Is a mapping of keys denoted by k here. So these are, keys that map to a location. So this is a location, or this represents a location rather. So a function h of k is a mapping of keys of, let's say, some values in a database to a particular storage location, right? So hashing functions map a large universe of keys like social security numbers or other values that need to be stored to a set of storage locations. Now, the important thing about hashing functions in general and good hashing functions is that they yield very few collisions. So now what is collision? Right? Essentially, no two keys are mapped to the same location by a good hashing function, right? So then only it's a good hashing function, but obviously that is not impossible, right? So two keys could be mapped to the same location by a hashing function depending on how we decided to formulate this function. And then we are supposed to find out the probability that no two keys are mapped to the same location by this hashing function. So essentially, we're looking at the probability of collision and trying to find out what is the probability that there are no collisions, right? So this is what it means, right? We just want to avoid collisions as much as possible, and the more my function does that, the better it is. Okay, so a few assumptions in this problem are that hashing function distribute keys uniformly, right? So there is a uniform distribution. So that's my first assumption. Uniform, this is an important assumption. Probability distribution. Okay, so that's one. The second one is that keys are selected uniformly as well. So let's say there are keys K1, K1, K2, K3, and so on. So these are all keys up to K of n. Either one of them could be selected, and then that selection is also uniform, right? Okay, so let's think about all the memory locations that are available to us. So let memory locations available to us be equal to m, right? So I have m locations available. Now again, when I add the very first record or very first value and map it to just any one location, there is that one location that's already taken, right? So any one location is taken out of these m locations. So now when we add the second record or the second value, the probability that it's mapped to a location different from the first one is given by m minus 1 over m, because there are still m minus 1 free locations available, right? Let me write it down here. Okay, so if we have m locations available, first record took one value out of m values, right? So then when the second record was added, the probability that it's mapped to a location different from the first one, now I'm interested in this probability, right? To avoid collisions, right? So the probability that this is mapped to a new location or a different location, new or different location from the first one, by the way, is m minus 1 over m, right? Similarly, for the third one, the probability that the third one is mapped to a location different from the first and the second one is m minus 2 over m, because 2 are already taken. So in general, right, the probability that the jth record is mapped to a free location after the first j minus 1 records have been mapped to hk of 1, hk of 2, hk of j minus 1 without collision. So probability for the jth record to like land without collision, mapped without collision, right? Which is the same thing as saying like a different location, is m minus j minus 1, because if this is the jth record, then j minus 1 are already there over m, right? Now, because keys are independent, the probability that all n keys are mapped to different location, let me denote that by p of n, would be m minus 1, the assumption of independence, right? M minus 2 over m, all these probabilities essentially, right? And so on up to m minus n plus 1. So I'm just like generalizing it, and I'm replacing j by n, right, for any n number of keys that I'm trying to find out. Okay, so therefore the probability that the question that asks is that there are no collisions, right? So no two keys are mapped to the same location by a hashing function is this, p of n. Now, additionally, I could also find the probability that there is at least one collision, and just it's a very simple addition to this problem. I could simply do a 1 minus p of n. So that essentially gives me that there is at least one collision, right? Now, our goal here is to find out the value of n for this equation here for a given value of m. Right, so again, using different techniques from calculus and even by doing a trial and error method, given an m, we should be able to figure out what n should be. And usually in problems like these, you'll be given some like threshold probability, and you might be solving for some given probability. You'd be solving for some n given some m, right? Or given like some other variation of the same problem. Okay, so that finishes the hashing problem. In the next video, we'll talk about something called a random walk.